Hello, I would like to thank the SPIE for hosting this session and talk, and I would like to thank you all for attending. I am David Compertore, and I'm going to go over our efforts in quantifying micron-level robotic movement errors using low-coherence interferometry. We did this process out of a desire to combine the functionality of non-contact low coherence interferometry with a general purpose robotic control. And the idea was to see how high of precision could we get with a general purpose robot. And we did that by tracking the movements over an optical flat. An optical flat is a well-known instrument in optics that has a known quality to it and is known to be quite good. In fact, our flat was 1/200th of a wave. So what we ended up with was a lot of plots and scans over many different parameters, and that's basically what I'm going to show you is a lot of plots and talk about them as we go through them. In the end, we'll give a lot of observations as I'm looking at those plots as well, but in the end we'll talk about potentials for its use as a system qualification and improvements and the best ways that you can maybe use a general purpose robot for metrology work. So general purpose robots are just that, general purpose. They're really not meant for metrology. They're not meant for robotic surgery. Now you would imagine, there are robots out there, those meant for surgery, which would be well controlled in their movements. They, would not have any errors or unexpected positioning movements in their movements as they move through the process. That's not what we have. And using a low coherence interferometry pen and precise metrology is not unheard of either. The UltraSurf does that quite well. It's a highly designed, highly engineered piece of equipment that gives incredibly accurate metrology data for ogives, missile domes, arcing optics, and that's, again, not what we're doing. We're trying to get as close, say, to a robot used in surgery or the UltraSurf with a general purpose robot to see how close we could get. What kind of errors would, if you did the same thing with a general purpose robot, what kind of errors would you expect to see? That's what these plots are hoping to suss out for us. So we did it with a simple setup. We took the optical flat and put it below the low coherence interferometry probe and then ran it with different in different directions at different distances at a bunch of parameters. In fact, one of the parameters is the reach, right? So robots, being general purpose, can reach different levels. Work near the base of the robot, if I'm the base, work mid-distance from the robot, or far reach from the robot base. And that's what you see in the diagram below the setup there. But let's continue with talking about the setup. Here we have all the parameters that we used in the setup. We did 3 different motions: linear motion, just a line back and forth. Circular motion, we asked the robot to circle around the flat, and arcing motion, which again is another circular motion, but now it's in and out of the plane or the tangential plane to the flat of the optics. Then we did, and for the linear, we did 2 directions, forward and backwards. We didn't do that for the other circular arcing. And then we did the 3 positions which I showed you earlier, near, mid, and far. We also did 2 speeds, 2 millimeters per second and 8 millimeters per second. We called them fast and slow. just to differentiate them. And you can see that we also did radial and tangential. So tangential is, as it shows in the diagram there, across from the base of the tangential to the base, the circle of the base. And radial is towards and near, back and forth from the base. And then the circular arcing path is also illustrated. Okay, so those are all the parameters. I'm going to jump right into the plots now. The next slide is for our linear tangential to the robot base measurements. So I broke it up into near reach plots, mid reach plots, and far reach plots. Those are the different columns. Slow and fast scans are the different rows. And then on each A, B, C, D, E, and F plots, there's repeated measurements. So we asked the robot to do it, and we took the data 5 times in the forward direction and 5 times in the reverse direction, and just overlaid them all into plot A, for example, where we're doing near reach, slow speed. So there's 10 plots for each of the 10 scans for each of the 6 plots up there. The first thing it shows us is that the scans, each scan is pretty repeatable. I mean, at least in quality, the peaks occur in the same position. I guess I gotta say, we didn't normalize the data to 0, so we didn't care exactly how high above the optical flat we were. And we also took out any tilt, so we detrended any tilt, because we didn't care how well we put the flat down on the base. If there was a little tip or tilt to that, we weren't worried about that. We just wanted to see how well it moved across the flat. And so we detrended those 2 things out of the data. So let's look at the total deviation saved. Peak to valley for the near reach is, for the slow scan, is about 150. For the mid reach slow scan, the total peak to valley is about 100, maybe 90. And then the far reach starts to get up there a little bit, maybe 350 total peak to valley. Maybe 200 if we did a little better detrending. And then for the fast scans, that's a pretty good repeat of what we had for the slow scans, and pretty much that's true all the way across. So speed maybe doesn't make that much of a difference. Definitely the reach, different reaches have different profiles, and repeatability though is good for everything, speed and reach, and forward and backward, because forward and backwards lay right on top of each other for the most part. Okay, so that's the linear tangential to the robot base. This next slide is linear radial to the base, and the first thing I want to point out again is that forward and backwards overlay on each other pretty well for the near and the far, but the mid shows a little, I don't know, we'll call it hysteresis, where there's a separation between the mid, the backward scan on the mid slow and the forward scan on the mid slow. Same is true for the backward scan, with the backward being above the forward scan. For the mid reach, you don't see that quite so much for the far, and you don't see it, actually you don't see it all for the far, and you don't see it at all for the near. We do have this little, I don't know what to call it, jitter, but the jitter is across many different scans, and it is, so it's real. It's not like somebody bumped something, because these scans are separated by several minutes, so those peaks have some systematic repeatability to them in the movement of the robot as well. So keep that in mind because we see it a little stronger later. We don't see it here though, but this is now the circular scans where we ask the robot to circle above the optical flat. Now it turns out that we asked it to do a bigger circle than the flat was, so we just caught a part of the arc. So this is a part of the arc of a circle that we asked it to move through, but it is in the same plane as the optical flat. Again, we detrended in the same way, normalized and detrended in the same way. You can see that the errors are in the same level, the 100 micron level, mid-reach a little more, maybe the 200 micron level, and then the far reach is starting to get up there, and that's almost a half a millimeter of deviation, both in the far reach, slow and fast. So asking it to work far reach and then do a more complex, I guess the circular motion is more complex, movement is stressing the system so that it doesn't stay perfectly in the plane that we're asking it to move in. Keep that in mind as we move to the next one, because now we're talking about an arcing motion, which is a circular motion, but in the plane perpendicular to the optical flat. And so what we did, we had to take the movement out. We knew what arc we were asking it to perform, so we just took that out, and this is the error from that arc that we're asking it to perform, which is true for the other plots as well, except for those are just linear movements. So this is the error to the arc we asked it to arc across. In general, it gave us the arc to this error. It gave us that arc well. So let's look at the error we have. So near reach is about 150. Speed doesn't seem to matter there again. Mid-reach is about 100, say, and at both speeds. And far reach is about 200 at both speeds. So this is the tangential arc, right? So it's moving tangential to and arcing at the same time to the base. The last plot actually is the radial arcing. So now it's moving back and forth from the scanning back and forth to the distance base of the robot. And the near reach has a total of 120 microns, mid-reach 120 microns, but far reach did a lot better at only about 100 microns if you ignore these spikes. But we're not going to ignore those spikes because those are real. That's many different, all 5 scans show spikes, and those scans are separated in time by several minutes, so it's something that's being repeated in the profile that we're asking the robot to move through. And that's happening at one speed. Actually, when you ask it for a faster speed, those errors go away. And you get a much more repeatable and smoother movement, even in the errors. So that's something to keep in mind. Speed a little faster, maybe a little slower, I don't know. Try different speeds. You might be able to eliminate these peaks. Were they near a singularity? I don't know. I think they would be near the same singularity at the different speed. So I don't know if it has anything to do with a robotic singularity. Doesn't seem like it because we're asking for the same positions. Robotic expert would know better than I would. But I think that's it for our plots. So let's talk about what we can guess at for whether or not we could use this robot as a metrology tool. Well, one thing we know is that different reach lengths have different but repeatable error profiles. And that repeatability is important because if it's repeatable, you might be able to back it out later, back it out from the data. Different speeds don't show different error profiles in general, especially for linear. Maybe, if you see that jitter though, you might be able to run at a different speed and eliminate that. So that's something to keep in mind. Back and forth motion is very repeatable. If you go left or right, doesn't seem to matter, so you don't have to worry too much about that. Errors don't seem to be related to vibration or instability. Great repeatability over many different scans, hundreds of scans. So doesn't seem like we have to worry about vibration or instability for the setup we used. Be careful with your setup, mounted well. And so it does seem possible that you might be able to remove errors later after you do the data collection because of this ability to maybe map the errors before you take the measurements. All right, I would just like to thank you again for attending this talk. Show you the group. There we are in our raincoats. That happens a lot in Rochester, that you need to wear a raincoat if you're not wearing a parka. So thank you again, and see you at the show.